What is the wavelength at which human body radiates maximum energy? Given B is equal to 2.898 into 10 raised to minus 3 meter Kelvin. Temperature of human body is 37 degree. And we have studied the Wien's displacement law, that is lambda m into T is equal to a constant, and this constant is called Wien's constant, represented by the letter B. And this lambda m means it is the wavelength at which the maximum emission of radiation takes place. Lambda m is the wavelength at which the maximum emission of radiation takes place, and T is the corresponding temperature, and B is the Wien's constant. In this equation, that is, as the temperature increases, lambda m shifts towards the lower wavelength region. As the temperature increases, the lambda m displaces towards the shorter wavelength region, and hence it is called the displacement law. Here in the problem given that B is equal to 2.898 into 10 raised to minus 3 meter Kelvin, and the temperature of human body T is given as 37 degrees Celsius, and on converting it into Kelvin we get 37 plus 273, that is 310 Kelvin. That is, T is given and also B is given. B is equal to 2. Okay, we have already written 2.898 into 10 raised to minus 3. So we can write the equation, that is lambda m should be, lambda m is equal to B divided by T. Considering the human body as a black body, the wavelength at which it radiates the maximum emission of energy, that is lambda m, is equal to B by T. Substituting the values, B is 2.898 into 10 raised to minus 3 divided by T is 310. We get 9.35 into 10 raised to minus 6 meter. And this is the wavelength at which the human body radiates the maximum energy. Calculate the change in entropy when 10 kg of water at 150 degrees Celsius is converted into steam at the same temperature. Given the latent heat of steam is equal to 540 calorie per gram. We have studied the equation for the change in entropy when a liquid is converted into vapor at the same temperature. Here, the water at 150 degrees Celsius is converted into steam at the same temperature, and so the quantity of heat required for the change of state from a liquid to its vapor at the same temperature can be written as Q is equal to M into L, where M is the mass of the liquid, here the mass of water, and L is the latent heat of steam. And then the change in entropy can be represented as, that is, change in entropy is equal to this Q by T. This is the equation. And here given that mass is 10 kilogram and the latent heat of the steam is 540 calorie per gram, and hence we can convert this mass also in expressed in gram, that is 10 into 10 raised to 3 gram. Both should be the same unit. And also the temperature T should be 150 degrees Celsius. is equal to, that is 150 plus 273 Kelvin, 273, and this will become 423 Kelvin. And we can directly substitute these values, that is change in entropy is equal to M is 10 into 10 raised to 3 gram into L is 540 calorie per gram divided by 423 Kelvin. And this will give the values as 12,765.96 calorie per Kelvin. And this is the change in entropy. And the next problem is the efficiency of a carnot cycle changes from 1 by 6 to 1 by 3 when the source temperature is raised by 100 Kelvin. Calculate the temperature of the sink. And we have studied the efficiency of Carnot's engine, and the equation representing this efficiency, eta is equal to 1 minus the sink temperature divided by the source temperature. And if T1 is the source temperature and T2 is the sink temperature, then the efficiency can be represented as eta is equal to 1 minus T2 by T1. And here the efficiency of a Carnot cycle changes from 1 by 6. Initially it is 1 by 6 to 1 by 3. That is 1 by 6 to 1 by 3 changes. That is when the source temperature is raised by 100 Kelvin. That is 1 by 3 will be when the source temperature, that is T1 is the source temperature, then this T1 is raised by 100 Kelvin. Then the value of the efficiency becomes 1 by 3. And then calculate the temperature of the sink. Here we are considering the efficiency in the two different cases. The first one is the case when the efficiency is 1 by 6. And the other case, second case is the efficiency is the case when the efficiency is 1 by 3. And the first case, the efficiency can be represented as eta, and the second case, the efficiency is eta dash. Let eta and eta dash be the efficiencies when it becomes 1 by 6 and 1 by 3. And here we can represent the eta as, that is, we are representing the eta as, the first case efficiency is 1 minus the sink temperature T2 divided by T1, and it is 1 by 6. And just rearranging this equation, that is T2 by T1 is 1 minus 1 by 6, and this will give 5 by 6, 5 by 6. That is T2 by T1 is 5 by 6. Therefore, the T1 can be represented as T1 is equal to 6 by 5 into T2. T1 is equal to 6 by 5 into T2. So the first assumption we get T1 is equal to 6 by 5 T2. That is, for the first case we are considering the efficiency as 1 by 6. And the second case, the efficiency we are considering it as eta dash. The eta dash, the efficiency becomes 1 by 3. 1 by 3. This 1 by 3 from the 1 by 6. And the source temperature is raised by 100 Kelvin increase ചെയ്യുന്നു. Then it becomes eta dash is equal to 1 minus T2, the sink temperature, divided by the source temperature is T1 plus this 100 Kelvin is equal to, it will be 1 by 3. It is 1 by 3. 1 by 3. This can be rearranged, that is T2 divided by T1 plus 100, and this becomes T2 divided by T1 plus 100 is 1 minus 1 by 3. 1 minus 1 by 3, and this will be 3 minus 1 by 3, that is 2 by 3. 2 by 3. Therefore, T2 is, therefore from this equation we can write T2 is equal to T1 plus 100 into 2 by 3. That is T1 plus 100 into 2 by 3, or T1 into 2 by 3 plus 100 into 2 by 3. This is the value. T1 into 2 by 3, or 2 by 3 T1, 100 into 2 by 3. Therefore, the T1 can be written as, this can also be written as, that is 2 by 3 T1 plus 200 by 3. But we know that what is T1? T1 from the first equation, T1 is equal to 6 by 5 into T2. Therefore, the LHS will be T2 is equal to 2 by 3 into T1 is 6 by 5 into T2. 6 by 5 T2 plus 200 by 3. 200 by 3. That is, this 3 and 6 will cancel. That is 4 by 5 T2. T2 is equal to 4 by 5 T2 plus 200 by 3. Or we can write that we can calculate this T2. T2 minus 4 by 5 T2 is equal to 200 by 3. T2 minus 4 by 5 T2 is equal to 200 by 3. Or 5 T2 minus 4 T2 divided by 5. It will be 200 by 3. That is T2 by 5. T2 by 5 is equal to 200 by 3. Therefore, we can calculate T2, and the value of T2 will be 333.3 Kelvin. This is the value of the temperature of the sink. Calculate the black body temperature of the sun. Given that Stefan's constant is 1.37 into 10 raised to minus 12 calorie per centimeter square per second. Solar constant is 2.3 calorie per centimeter square per minute. Radius of the sun is 3.5 into 10 raised to 10 centimeter. The distance between the sun and the earth is 1 into 10 raised to 13 centimeter. We have studied the equation temperature of the sun T is equal to R square by R square S0 divided by sigma the whole raised to 1 by 4. Here the R is the, small r is the distance between the sun and the earth. Small r is the distance between the sun and the earth. And capital R is the radius of the sun. Capital R is the radius of the sun. And S0 is the solar constant. S0 is solar constant. And sigma is the Stefan's constant. Sigma. So here R is the, small r is the distance between the sun and the earth. And capital R is the radius of the sun. and S0 is the solar constant, and sigma is the Stefan's constant. That is, here the small r is given as 1 into 10 raised to 13 centimeter. Here the units are in centimeter and in calorie. So I think no need of converting it into meter because all are in the same unit. That is, R is equal to 3.5 into 10 raised to 10 centimeter. And the solar constant S0 is given as 2.3 calorie per centimeter square per minute. So we can convert it into calorie per second. That is 2.3 divided by 60 calorie per centimeter square per second. And the Stefan's constant sigma is given as 1.37 into 10 raised to minus 12 calorie per centimeter square second. And substituting these values, we get small r is 1 into 10 raised to 13 the whole square divided by capital R 3.5 into 10 raised to 10 square. A0 is 2.3 divided by 60 divided by sigma is 1.37 into 10 raised to minus 12. The whole raised to 1 by 4. Therefore, finally we get the value of T as T is equal to 6913 Kelvin. That is, the temperature of the sun is 6913 Kelvin. And the last question is, a Carnot's engine whose temperature of the source is 200 Kelvin. It takes 100 calorie of heat at this temperature and rejects 75 calorie of heat to the sink. What is the temperature of the sink? Calculate the efficiency of the engine. And here, given that is the temperature of the source is given, it is taken as T1 and T1 is given as 200 Kelvin. And the corresponding heat Q1 can be written as 100 calorie. And Q2, that is the quantity of heat rejects to the sink, Q2, that is already given, Q2 is equal to 75 calorie. And we have to find out the T2, temperature of the sink, and also the efficiency. We have studied the efficiency, it is equal to 1 minus sink temperature divided by the source temperature, T2 by T1. And first we have studied the equation, that is the source temperature and sink temperature and the quantity of heat which are taken from the source and projecting into the sink. They are related by the equation Q1 divided by T1 is equal to Q2 divided by T2. Q1 by T1 is equal to Q2 by T2. So we have to find out the temperature of the sink. T1 is the temperature of the source, T2 is the temperature of the sink. Therefore, T2 will be that is T2 is equal to T1, that is T2 is equal to T1 into Q2 by Q1. That is T2 is equal to T1 into Q2 by Q1. Here T1 is given, T1 is 200 into Q2 is 75 divided by Q1 is 100. And this will get about 150. We get 150. That is 150 Kelvin. And next we have to find out the efficiency of the engine. The efficiency eta is given as 1 minus T2 by T1. That is 1 minus T2 is 150 divided by T1 is 200. And this will gives finally a value, that is minus, that is 1 by 4, that is 0.25 eta. That is the efficiency is, therefore the efficiency of this engine is 25%. That is efficiency is 25%.